Hey guys, Command here, and today I'm going to be showing you the basics of operations research, more specifically the Simplex method. So, what are some of the key words that come to mind when we're talking about operations research? Well, the first thing is we have an objective function. Now this can be something such as we want to maximize z, which is equal to 3x1 plus 5x2. Alright, so this is our objective function. Now the name gives it away. Objective. What is an objective? It is a goal that you are trying to achieve. Now our goal in this scenario is we want to find the maximum value of z. And what we are going to do is we're going to look at these decision variables. x1 and x2 are set to be decision variables. Why are they decision variables? Well, they are the ones that we're making the decision about what their value should be. Now, they are critical because they are what form part of the objective function. So we want to maximize z, which is a function of x1 and x2. And x1 and x2 are said to be decision variables. Now, another term that is important is that, notice if I just gave you this to maximize z is 3x1 plus 5x2, you could give me any value of x1 and x2, and in fact you could claim that they go to infinity, z tends to infinity. Now, this is where our interesting part comes to play, and this is the constraints that we impose. Constraints. And normally what you'll see in literature is that they will say ST, subject to. And in this scenario, let me use the example of saying x1 must be less than or equal to 4 and 2x2 must be less than or equal to 12. Now, I'm going to introduce briefly a few important concepts regarding these constraints and these signs, the inequalities that you see on the right hand side. Some of you may be familiar with the term, but whenever we see a less than or equal to sign, we want to add a variable, and that variable is called a slack variable. So, these we add to make the less than or equal to an equal to sign. So, in this, and they're commonly denoted by SI, and for this one, since we're talking about x1, I'll simply refer to it as, we're going to say x1 plus s1 is now equal to 4. So this is the purpose of a slack variable. It's to introduce a variable so that we have sufficient degrees of freedom to be able to do the simplex method. Now, this example is rather simple. There's simply a less than or equal to sign. But if we are facing a greater than or equal to sign, in this scenario, then we have to subtract an excess variable. And I like to personally denote that as EI, wherever the I corresponds to whichever row you are in. So let's say I had x1 has to be greater than or equal to 5. Then I would say x1 minus E1 is now equal to 5. But there is another problem that arises from this scenario, and that's why I'll refer to it later in more specific detail. But since we've subtracted the excess here, we also need to add back an artificial variable, and these you will commonly see denoted as AI bar, or in this scenario I'd refer to it as A1 bar. And this will be explained later on a section on the big M method and the two-phase method of operation of the simplex method. But for this scenario, I just wanted to mention what happens in the scenario that we have a greater than or equal to, or a less than or equal to, as I've shown here. Now these are just the very basics to get us started with this objective function and the constraints. Alright, so when I want to do the simplex method, there are a few things that need to be done, and I'll list out those steps for you here. Simplex method, or the simplex algorithm. So, step 1. Identify the entering variable. Step 2. Carry out the minimum ratio test. And then step 3. Again, check if the solution is optimal. Now I'll define optimality to you in this scenario when I'm working through the example, but just you can think of optimal as your best attainable. So these are the 3 steps, and if you've done these 3 steps and you come to step number 3 and you realize that your solution is not optimal, and I'll define that now. If that is not the case, then you have to return to step 1, and then you work your way through to 3 again. So, referring to the example that I stated earlier in this video, we want to maximize z, which is equal to 3x1 plus 5x2, subject to x1 being less than or equal to 4 and x2, 2x2 being less than or equal to 12. So what we do is we go add our slack variable, so we transform this to x1 plus slack variable 1 must be equal to 4. This becomes 2x2 plus s2 is equal to 12. Now, how I'll do this simplex method is one of the most efficient ways is when you're just starting this is to write it in a table form. So I'll list out the columns for x1, x2, slack variable 1, slack variable 2, and then here we have our right hand sides of the equations. So we want to maximize z, which is equal to 3x1 plus 5x2. So if we bring the 3x1 over and the 5x1 over, we want to maximize z minus 3x1 minus 5x2. So these negatives we can go right here as our 0th row. So x1's coefficient is negative 3. x2's coefficient is negative 5. Slack variable 1 is 0. Slack variable 2 is 0. And our right hand side is initialized to 0. Now, with the following 2 rows, we simply input our constraints of x1 plus s1 must be 4. So here in x1's column we put 1, there's no x2, there's 1 for s1, 0 and 4. Then we have for x1 0, x2 2, s1 0 and s2 is 1. And then our right hand side is 12. Now, to check for optimality when you have this initial table or tableau, however you wish to refer to it, this initial table, we look at our 0th row, and in this 0th row we see that the coefficients of the decision variables are negative. A solution is only optimal if and only if, hence the 2 F's, all entries in row 0 are greater than or equal to 0. And since they are not, then we have to go and identify the entering variable. Now the entering variable is the variable that we say will enter the basis. It's the one that's going to have some value assigned to it that is non-zero. And how we determine it, to determine the entering variable, we look at these coefficients. The most negative one, or you can think of it as the one that has the greatest absolute value, and in this scenario it's clearly x2, which with -5, as -5 is smaller than -3. So this column indicates that x2 will enter the basis as -5 is greater than the absolute value of -3. So this implies that x2 is entering. Now, we have to do something called the minimum ratio test. That is step 2. Now the minimum ratio is, well, obviously it's the minimum of some ratio. Well, what is that ratio? That ratio is the ratio of the right-hand side to the coefficient in the column of the entering variable. So we're going to take 4, and we're going to look at the column of x2, and since we see here is a 0, this is inconclusive, so this one we will ignore. Then the second one, we see it's 12 divided by 2. So we can see clearly that this row is the only row that can actually leave, because your minimum ratio test will only be carried out if the column itself is non-zero. Because if we divide by a negative variable or we divide by 0, then we can move this value to infinity on the decision variable side. So all you need to know is that when you're looking at the column to determine the leaving variable by doing the minimum ratio test, you just look at the positive entries of the column of the entering variable. So in this scenario, it's only this variable. So thus we have determined that S2 must leave the basis. And here normally it's good practice to write BV for basic variables, so S1 and S2. Now, a basic variable and a non-basic variable. These are the definitions. A basic variable, well, it's basically set equal to what's on the right hand side. And in this scenario, if we look at the column, at the table, we see that S1 and S2 are in the basis, as their coefficients are 1 and 1 respectively. And normally when we initialize the simplex method, we set these slack variables, we set them equal to being the basic variables. So they are simply set equal to the right hand sides. So in this case, S1 is 4 and S2 is equal to 12. Now the non-basic variables, they are the variables that are set equal to 0. Set equal to 0. So in this scenario, if we look at this initial table, we can see that as I have specified S1 and S2 to be basic, that means that X1 is going to be 0 and X2 will be 0 as well. Alright, so this initial tableau, I just want to specify and make it very, very clear to you. The basic variables and the non-basic variables. So, the basic variables in this case are S1 and S2, and they have the values 4 and 12 respectively. The non-basic variables are X1 and X2, and they are set equal to 0 and 0. That's just a definition. Non-basic variables, think of it, non-basic always 0. Basic variables are basically just set equal to what the right hand side is in the table at the moment. So if you look here in the table, we have determined by the minimum ratio test that slack variable 2 must leave. And x2 must become basic. So it's set to enter the basis. So now we need to use simple row operations. Now we need simply to use row operations to set this 2 to transform it to 1, because that's what we do in Gaussian elimination, is to make this coefficient 1 of your variable, which is in the pivoting column, and then we will have our new row 2. So as we see this entry is 2, we simply say a half row 2 to become row 2 new. So once we have done that, we can simply see that it's 0, 1, 0, a half, and then 12 over 2, 6. Then we can write the other rows, fill them in, bring them down, and then so when we are pivoting, we need to make this column, the column of the entering variable, we need to make all entries 0 above this one. So this one is your reference. You want to have it having a value of 1, and all other entries in the column above it must be 0. So row 0 here clearly has a negative 5 in this column, so we're going to have to take row 0 and we're going to have to add 5 times row 2 new, because negative 5 plus 5 is going to give us 0. So the transformation leaves us with negative 3, 0, 0 plus 0 is 0, 5 over 2, and then over here we have 0 plus 5 times 6, which is 30. So this is how we go about the first iteration. This is said to be our first iteration. And now let me just list out the basic variables that we have. So in this scenario we still have S1, but over here we have made X2 basic. And now again we refer to the steps of the simplex method. Step 1, identify the entering variable. Carry out the minimum ratio test. Step 3, check if the solution is optimal. Optimality is only achieved if all of the coefficients in row 0 are greater than or equal to 0. And we can clearly see that this is not the case, as x1's coefficient here is negative. So what do we have to do? We repeat the steps of the simplex method. x1 must enter the basis, so we know this is the column that will now enter the basis. And now we carry out the minimum ratio test. So ratio of 4 to 1 is 4. As this entry is 0, this minimum ratio test would be inconclusive. So we can clearly see that this row is the row of the leaving variable, and in that scenario we are referring to S1 must leave the basis. And as this is the case, we need to again start with our reference row, which is row 1, and as the entry here is already nicely written as a 1, there is no need to do any row operation on row 1. As is this is 0, so there's again no clash or problem, no need for another row addition or subtraction. And then here for row 0, this is negative 3, we want to make it 0, so we're going to have to say row 0 plus 3 times row 1 to become row 0 new. So negative 3 plus 3, 0, 0, 3, 5 over 2, and 30 plus 12, 42. Now, check for optimality. And you'll notice that all entries in row 0 are greater than or equal to 0. So optimality is check, and our basis, what are our basic variables? x1 and x2, and they're equal to 4 and 6 respectively. Thus our optimal solution in terms of the original decision variables is 4 and 6, and the maximum value of z that we can attain is 42. So this is the very basics of the simplex method, how to do it and how to run through it. This is a very simple example, and I hope that I've helped you to gain a better understanding. And again, if there are any issues, any problems, then just ask me, write a comment or so. So I just like to go through the keywords that we focused on. The very first one, objective function. The goal you're trying to achieve. So in this case, we wanted to maximize z. The decision variables, these are the variables that we're making the decision about. x1 and x2. And then we had our constraints. We had x1 has to be less than or equal to 4 and 2x2 has to be less than or equal to 12. I talked about the slack variables, which we need to add to make the less than or equal to sign an equal sign. Also to briefly mention the excess variables and the artificial variables, which I'll talk about later. Then I talked about essentially the 4 steps of the simplex method, identifying the entering variable by looking at the row 0 variable with the most negative value, carrying out the minimum ratio test, which is the ratio of the right hand side to the entries in the column of the entry variable, but only the positive entries. And then I referred to checking again if the solution is optimal. So simply checking if the row 0 coefficients are all greater than or equal to 0. And then if that condition is not met, you simply start over again, identifying the entering variable, carrying out the minimum ratio test, and you carry on until you have ensured that your solution is optimal. So, thank you very much. Have a nice day.